So let's try problem 818 on page 403. I like it because it looks interesting to me. Have you guys ever seen the way that they move dividers on a highway? You know, the concrete dividers that are movable, and how they've got those clamps that when you pull up on the clamp gets tighter or whatever. That's kind of how this works. And so I saw this problem and thought, oh, that looks interesting. So we've got some mass. The mass is 150 kilograms. And there's a whole gripping structure that looks something like this. And I guess I should include the fact that there's feet connected here. And despite my drawing, it's all symmetrical. I know my drawing's not very good. And of course there's dimensions given and so forth, and the different, I guess I could name some of these points. B, C, D, E, and F, and perhaps an, well, where's G? They just went for A. I guess they didn't use G because they used G for the center of gravity of the grid. So first things first, how much is force P, and how would you know?
It has to be equal and opposite to the weight of G, right?
In other words, an overall free body diagram tells you that however much the crate weighs is however much is the same
We're supposed to
amount.
ignore the
that
weight
P.
of the clamp.
We're ignoring the clamp weight, that's correct. And remember the illustration I gave you a moment ago, if you're thinking of a front-end loader or some type of moving machine, a loader picking up a concrete block, the 20-pound weight of the clamp or so is nothing by comparison to the 1,500-pound piece of concrete. So yes, we are neglecting the weight of all this structure around it, okay? How much weight is there?
150 times 9.81.
Good, I was afraid you were going to stop at the 150. It's not 150 kilograms, it's 150 times 9.81 meters per second squared. In other words, in newtons, the weight is about 1,500 newtons. Not quite, because 9.81 is a little less than 10. But if you don't mind, go ahead and tell me what 150 kilograms times 9.81 meters per second squared comes out to, and that will be our raising force P.
1,471.5.
Thank you. And those, of course, are newtons, okay? How come sometimes we have to multiply what's given by the acceleration of gravity and sometimes we don't?
Depends on what it's given as.
Depends on what's given. If mass is given, you must multiply by G, right? Now, if you multiply, let's just pause for a moment because I know this is actually metric. Let's just pretend that they gave us 150 pounds mass. Once you multiply it by G, the acceleration of gravity, which is 32.2 feet per second squared, what do you get?
Pounds force.
You don't get pounds force. You get pounds mass feet per second squared, which are a valid unit of force. And it'll be a larger number than the equivalent pounds force. In fact, 150 pounds mass will weigh 150 pounds force.
Ah, that's right.
But you have to multiply by 32.2 feet per second squared, then divide by 32.2 pounds mass feet per second squared per pound force in order to calculate the pounds force, which is confusing because it's different in metric than it is in English. What's that?
It's just a 1-to-1 ratio.
Right, so that's what gets confusing, is that in the English system, if I give you a mass in pounds mass, the weight is simple, it's just that same number in pounds force. Because that's the net effect of multiplying by G and dividing by G sub C. But in metric, if I give you a mass, you have to multiply it by the acceleration of gravity to get a different number for the force. Okay? So, as usual, the English and metric systems are opposite in every way possible. Okay? I guess it's just to confuse students. That's probably a good reason to make them that way. Anyway, so a little under 1,500 newtons is the force required to hold this in equilibrium, but that's not really the question. The question is, determine the least coefficient of static friction at the pivot blocks so that the crate can be lifted. In other words, the pivot blocks are these things down here. And they look more like this. So we're supposed to determine basically the friction coefficient so that the block can be held in place. Okay? Why would we care about that?
So we can know what material we gotta make the clamps out of.
Absolutely. Different materials have different friction coefficients. You make this out of UHMW. Do you know what UHMW is? ultra high molecular weight, what, polyethylene, I think, PE, UHMW? It's common plastic that's used because it has good, well, low coefficients of friction. So it's really common. In fact, you can get UHMW tape to put on surfaces to make them more slick. It's not like quite like Teflon or an oiled surface, but it is certainly less friction. Anyway, you might have to put some grippy material here, maybe sort of a rubber or something, right, to get a higher friction coefficient. And of course, you'd have to glue it to the foot to make this work. But anyway, or you could screw it to the foot, actually. If you have a thick enough pad of rubber, you can attach it to something with fasteners. So we'd like to know how much friction coefficient is required in order to generate enough friction so that this normal force is adequate to hold the package up, right? Notice I wrote friction equals mu S N. Why did I do that? I thought it was less than or equal to. I thought this was the proper equation. Of course, that's not really an equation, it's a comparison, right? It's an inequality. So how come I wrote equals? Did I make a mistake?
Because it theoretically,
We're trying to find the least, right? What's the minimum friction coefficient? In other words, so that friction is at its maximum and doing as much as possible, okay? How do you suggest we proceed from here? It's actually very much like the problems you've been working so far. This is almost a frame, isn't it?
free body diagram.
Free body diagram, good, of what? Let's just start with the weight itself, the crate, okay? We know we got 1471.5 newtons. So how much is the friction on each side? Half of that. What is half of 1471?
735.75.
Thank you. So we know that we need a frictional force of 735.7, we could call it 736 newtons, would probably be okay. All right, we need that much friction force on each side. Could we calculate the normal force required? Well, the problem is we don't know the friction coefficient, and that's what relates the friction force to the friction coefficient. But at least we know the magnitude of the friction, right? Now it looks like we've got a problem here because we've got two unknowns. What do you suggest we do from here? Let's draw another free body diagram. Why not have plenty of them? What's that right-hand side, I don't know what to call it, toggle, clamp, edge, something? Notice that they set it up so that the vertical distances are the same. It's 0.5 meters. I think it's 500 millimeters is the way they specified it. But this is a toggle, and what it tells you is that whatever force there is here will be equal and opposite here, right? For it to be in equilibrium. I mean, you can tell that just by inspection. Think about summing moments about point D. Obviously, point D, that rod in the center is holding the whole thing together. Without that rod in the center, it all just falls apart. But it's pretty easy to see whatever this force is, there's twice that here. And it's pretty easy to see they're equal because of thinking of summing moments about this point. Notice I'm not writing down every single equation anymore. I'm thinking through it, kind of like what we just did with our practice test. Okay. Now, of course, the normal force there and there on the foot have to be the same. And so P is the normal force that I'm interested in. So basically what we've done is we've come to the point where we can analyze member HF, for example, or EH, it doesn't matter, it's symmetrical. And so what's really interesting now is the fact that this member, HF, bless you, is applying a force, it's going to be something like that. Of course, that's not really right, is it? Now I've got to think just a little bit because let's do it this way. Here's the problem. I know HF is a two-force member, so I expect a force along that direction. So let's pause on this in just a little bit. Maybe I'm flying a little too fast. Let's try again. How about if we go from here? We know this force. So couldn't we calculate the force in this member? That should be easy. So how would I do that? Well, let's see. I guess the easiest way to do it is to take a free body diagram with pin H. So let's see, there's a force P here, and I shouldn't have said P, I'm sorry. I meant a generic force here. I'm sorry, I didn't mean to confuse with that. All right, so let's see, I guess we'd have to have force like that to hold the pin in equilibrium. So let's just call this HF. And so we know the angle is a 30-degree angle here. So let's just calculate, what do you think? Some force is an X or Y? And why?
Some forces, wouldn't have to be both.
Sum of force in X would just tell us that these two forces are equal to each
Yeah.
other. So I think summing forces in the Y direction will be more beneficial. So let me, I guess I'll erase this for the time being. So summing forces in the Y direction, I'd have P minus 2HF, but I want only the vertical component, so would that be the sine or cosine side? It's the sine side of the angle theta. And the sum comes to 0. So, calculating HF, I would have, let's see, that'd be P on the other side of the equation, divided by 2, divided by sine of theta. Of course, P is 1471.5 newtons. 2 is just a number, sine of 30 degrees. So tell me what the force is in HF, if you will, please.
1471.5.
Oh, okay. So I guess sine of 30 is a half then, huh? So now we know the magnitude of force in HF. All right? So, I think what I'd like to do is take only the horizontal component of that force. Now here's where I'm a little bit worried. If we sum moments about point D, I may have to be a little more careful than what I was a moment ago. Let's try again. So I'm going to take another free body diagram of that arm on the side. Okay, so this is FDB. We know that the force applied, 1471.5 newtons, is applied at a 30-degree angle. And I don't know if this is perpendicular to FD or not. Let's see if we can figure that out quickly. We know that the run is 275 millimeters. I think that's what it was. I'll check it again here in a minute. And then 500 millimeters, or a half of a millimeter, or half of a meter this way. So do me a favor, if you would, calculate this angle here. I probably shouldn't call it theta. We've already used theta. How about alpha?
Is it 2HF?
Why are there two? Because HF also acts on the other side, but it's of course EH. But they have to have the same magnitude. That's right, EH. Because of a sum of force in the horizontal direction. Yep. Good question. So what are you going to use since you've got a rise and a run? You're going to use tangent. Exactly, inverse tangent. So we need the inverse tangent of 275 over 500. What do you get?
It's 28.8.
28.8, almost. All right. Well, I guess the easiest thing to do then is to calculate, well, let's leave that. Actually, you know what? Let me change the meters. I prefer to work in meters if possible. So I think what we will need to do is sum moments about point D, because notice that this foot can only have normal force, right? This is a 2-force, well, it's not a 2-force number. Again, I may be wrong in my thinking.
Can you not just take the cosine 30 part of the 1471?
We're going to do that. We're going to break this up into two components. I'm trying to think ahead and figure out if there's a vertical component of force here that I need to take into account. I think what will happen is just the normal force will move to wherever it needs to, so that the combination of the normal force and the friction force, which would be a vector something like this, so we move down, we'll pass through. Did they give us a height of the foot? They did not. Okay. So I'm trying to make sure that I don't end up with some component of force in the vertical direction, or maybe I should. But yeah, let's go ahead and calculate the horizontal and vertical components of this force. So 1471.5 times cosine of 30 degrees, in other words, 0.8, I think 0.86 something, gives us how much force in the horizontal direction of this force. So 1471.5 times cosine of 30 gives us how much?
1274.36.
Okay, and how about the vertical component? So a half of 1471, we already had that, it was 735.75. There we go. All right, I think I'm okay now because, look, the only vertical component of force here would be this 735.75, which is equal to the friction force on that side of the box. So I think we're okay. Yeah, so we would have a force down here of 735.75, and then a normal force of 1274.36 newtons, okay? Make sense so far? Any questions? So I think now we know the magnitude of the normal force because this is just going to be applied through the foot. And then this force is what's going to counteract the friction force on the foot body. And of course, we've got a couple like this, and the normal force is going to end up down there, so they'll have to cancel each other. So we'll have to have enough foot for this to work, but apparently there's adequate amount or adequate length from here to here. So I think we're set. All we have to do is just take the ratio of these two, because look, what we've done is we've calculated the normal force now. So the friction coefficient would have to be the friction force divided by the normal force. And we know the friction force has to be, some of this, we don't need it anymore. The friction force has to be 735.75 newtons, and the normal force is only 1274.36 newtons. And so once we take that ratio, we'll have the friction coefficient. Yeah, did I miss something?
Does it matter that B is 300 millimeters away from D, or from
Oh, did I miss
from
that?
D and not 275?
Oh, you're right. You're right. That's a different dimension. Okay, so the magnitude of the normal force may be different. Is that going to make a difference? I don't think so. Well, no, I do. You're right. Rats, I didn't notice that. Okay, I'm going to have to try again then. It's going to be really close to that ratio, but not quite. Thank you for pointing that out. So, let's see, what do we know that's true then? We broke up this force
So all those numbers up top
into
are
these two,
correct.
so these are okay.
Well, wouldn't the X still be 1274.3?
I think the X still does, because if we sum, the only problem is when we sum moments about D, notice that this force has a different moment arm than this force. Now, because of summing forces in the vertical direction, notice that CD can't apply any vertical force, right? So summing forces in the vertical direction tells me that this component is 735.75, right? So now to calculate this force, which is the normal force, it is going to be a little different than that. Because what I have to do now is sum moments, and I think the easiest point to sum moments is about D. Counterclockwise positive. And so there we'll have what? Two negative forces here. So negative 1274.36 multiplied by 0.5 meters. I guess I should put units in here to make it clear. Newtons times 0.5 meters. Okay, that's the moment of this force at F about D. The moment of the vertical force would be minus 735.75 newtons multiplied by its moment arm, which that was the 275 millimeters, so 0.275 meters. And then we'll have a longer moment arm for this force, but that is causing a positive moment. So plus 735.75 newtons multiplied by the moment arm of, what did you say it was, 0.3 meters?
Yeah.
3 millimeters? Thank you for pointing that out. Now the vertical distances are the same. And so this normal force will have a positive moment N times, and unfortunately we're using the symbol N for newtons and N for a force, a normal force, but oh well. And so that force will be,
What time?
Yeah, the moment I was 0.5 meters, thank you. And that sum had better come out to 0 for this arm to be in equilibrium. So once we calculate this normal force, it's gonna be really close to 1274, but because of that offset difference, it'll be a little bit away from. So what does the normal force come out to in magnitude?
I got 1237.57.
Anyone second that? Seems reasonable to me because notice this number is positive and this one's negative. Of course, this one's a little bit bigger. That means we end up with a little bit more positive in this equation, which when we move to the other side will be negative, so it's going to take away from this, which means the normal force should end up being slightly smaller than 1274. Which is kind of interesting because I guess what that means is that if you move point B over even farther, more than even 300 millimeters, you might be able to reduce the normal force even more. Or move it the other way and you could increase it. Which makes sense. But anyway, so there's the normal force. Now that we've got the normal force, again, all we have to do is take the ratio. Let me get rid of this foot because we don't need it anymore. All we have to do is take the ratio of the friction force to the normal force. And we know the friction force has to be 735.75 newtons. The normal force we just calculated at 1237.57 newtons. So that ratio would be the static friction coefficient. So what do we get? Unless I missed something else, which I think we're okay at this point.
0.595.
So about 0.6. So that would be the minimum friction coefficient to hold this box in equilibrium. Do you think that here's another question for you, do you think the mass of the box makes any difference? You do?
No,
You
because
just increase
it's,
the
more you
normal
Exactly.
force have to increase.
Notice that this is proportional to the mass, isn't it? All of these things, therefore, are proportional to the mass. So the actual mass wouldn't have had to be given for us to calculate this friction force, or this friction coefficient.
Just a mass.
Just a mass. Anything.
Yeah.
Any other questions on this problem? Thanks for correcting my mistake there. Appreciate it.